Uh, Thanks for coming. So today I'll be presenting about VQE for excited state. In my previous presentation, I talked about using VQE to calculate ground state energy of molecular systems, how to use VQE to calculate ground state energy. And in this presentation, I'll just show how to extend the VQE framework to calculate the excited state energies. So, uh, so the contents of this presentation is first I'll just give a brief overview and review on VQE, and then we'll introduce some two algorithms used to calculate excited state energies by extending the VQE framework, the variational quantum deflation algorithm and the subspace search VQE. And finally, I'll just talk about a little bit about using some symmetry constraint to find a specific eigenstate of interest of a given Hamiltonian operator. Yeah, so this will be the content of this presentation. Okay, let me start with VQE. What is VQE? It's a variational quantum algorithm which got a lot of attention these days. And it has been one of the most promising way of approaching quantum chemistry application problems on a near-term device. And generally, it's used to calculate the ground state energy of a given quantum mechanical system. And if we see its mathematical meaning, we can just consider it as an algorithm used to find the lowest eigenvalue of a given Hamiltonian operator. And it's based on the variational principle of quantum mechanics. And it gives us the upper bound on the lowest eigenvalue of a Hamiltonian. And what makes VQE to be suitable for NISQ device? First, we have fully quantum algorithm called quantum phase estimation. What happened? Is it a connection problem? Nope, it's not here. Sorry for the mishap. Okay, yeah, we have a fully quantum algorithm for determining the eigenstates of a given the eigenvalue of a Hamiltonian operator, the quantum phase estimation. A quantum phase estimation, it allows us to find the phase or eigenvalue of a certain unitary operator, having properly prepared trial state. The problem is that it requires a lot of gate tapes, a lot of qubits and a larger gate tape. So the only way we can use this kind of application for solving chemistry problems or any others as on a NISC device or near-term devices using VQE. That's one of like the most promising or like way of using it. And if we see the pipeline or the total algorithm, first we have a certain problem, and that problem is described with a Hamiltonian, and that Hamiltonian might be described in a different form. So in order to run it on a quantum computer, it has to be mapped into into a qubit Hamiltonian, which is sum of like a weighted sum of Pauli operators or Pauli words. And then the other step was just preparing the trial state. Using some sort of ansatz, we kind of prepared a trial state that corresponds to the ground state of the given Hamiltonian. We just prepare that state using an ansatz, which is a parameterized quantum circuit, and we measure the expectation value of the prepared Hamiltonian operator. So these parameters are they're optimized on a classical computer through some optimization methods. And yeah, and here it's kind of one important thing is these preparing there are two major bottlenecks in the VQE algorithm. The scaling of the ansatz and also efficiently measuring this Hamiltonian operator. The ansatz could be of different form. It could either be like a chemistry inspired ansatz or like hardware efficient ansatz. Both of them, they have like their own advantage and disadvantage. And there are also some ansatz that kind of breach both, like that are both hardware efficient and like a little bit of chemistry inspired or problem inspired ansatz. So yeah, like there are many things to study in this VQE algorithm. And one major thing is in order to extend this framework and for practical application, only calculating the ground state energy of certain Hamiltonian is not that important. We need also some excited states, and in order, if we're approaching to the the application, we need some more things we need to calculate. But this VQE calculating the ground state energy could be the first step, so it's kind of bottleneck for the whole problem. So it's kind of relevant to study more about it. And so yeah, there are a lot of methods actually proposed that are used to extend the VQE, the previous VQE framework in order to calculate excited state energies. And these two papers suggest different algorithms. The first paper that suggests variational quantum deflation algorithm, and the second one suggests subspace search VQE that I'll talk about later. And there are also other methods, but if we choose those algorithms that doesn't change the VQE framework match, those are the two important ones. So yeah, let's see about the variational quantum deflation algorithm. So here, this algorithm is just it has it's similar as the VQE, but there's a minor extension on that, which is it includes in the cost function, there's an additional term included. So initially, when we do the VQE, we prepare a trial state, which is prepared by applying a certain unitary transformation. So applying a certain gate from our initial state, we prepared the trial state, and then here we can see that it's measuring the expectation value. So the Hamiltonian is written as a weighted sum of Pauli operator, and the expectation value is calculated. And here we can just get the expectation value of the given Hamiltonian operator. And what we need now is excited using this, like using this only states, we can calculate the ground state energy. But if we want to calculate the second eigenenergy of the Hamiltonian, we need to go one more further step. So how we do that is, first we calculate the ground state energy, and then we run this algorithm. What the additional term is kind of an overlap term, which is it's a penalty term. We search for a state that is orthogonal to the ground state energy. So if they're orthogonal, then like the state overlap is going to be 0. So if we try to minimize this cost function, we'd be able to find the next eigenstate, or then the next ground state, the next like lowest eigen value of the Hamiltonian. And through an iterative process, we can just run this algorithm again and again and find all like the k eigenvalue of the given Hamiltonian operator. Okay. By the way, if you have some question, just feel free to stop me on the middle rather than waiting until the presentation is over. Okay, yeah, so this is all about the variational quantum deflation algorithm. So one thing in this algorithm, or in this cost function, we see is there's beta term here. This is actually the expectation value measurement, but here we calculate the state overlap, and we have a certain hyperparameter here. So finding that hyperparameter is kind of one problem. So how do we determine beta in this? If we sufficiently choose a larger beta, this cost function is going to be, if we do the optimization, it's going to force like the eigenstates to be orthogonal to the previous state. But choosing sufficiently large beta has its own cost. What is the cost of choosing large beta, sufficiently large beta? Is that the sampling cost. So when we do this kind of algorithms, or when we simulate this on an actual quantum computer, we get expectation value through some sort of samples. So and it's really important to make sure that the number of samples that we are the number of sample has to scale reasonably to just achieve some sort of like to be useful, or to have some speed up compared to the classical algorithm. So if you see the VQE, the sampling cost, or the number of samples we need to perform in order to get a certain precision, is given by this equation. Actually, yeah, we can give this relationship from the Pauli Hamiltonian. DCIs are the coefficients of the Pauli Hamiltonian. For the Hamiltonian is written as a weighted sum of the Pauli operators, and CJs are the coefficients of each Pauli term. And then, like, yeah, if we calculate the variance and calculate the precision, or like the variance, or the how precise it's going to be having a certain total number of measurements, we can get this kind of relation. And so, yeah, so the total number of measurement needed to get this precision is given by this relation. And for VQD, since we have beta, then the total cost of sampling is going to be given by this equation. So choosing sufficiently large beta has its own problem. So what we need to do is to have an educated guess for these beta values, so that like the cost of sampling will be relatively close to that of VQE. So how do we choose a beta or beta I? So in order to choose a beta or beta I, like we can just view the Hamiltonian in this form. Actually, yeah. One way of finding the excited state energy could be by like just without modifying the Hamiltonian, just adding a certain penalty term on the cost function, and then just doing the optimization loop. But like an equivalent viewpoint for this problem could be we can deflate the Hamiltonian, or we can just modify the Hamiltonian in this way, and then if we try to find the lowest or the ground state of this Hamiltonian, it corresponds to the case excited state of the original Hamiltonian. So yeah, these are like equivalent viewpoint, because if if you have a given state of like this, and we try to minimize the expectation value of this Hamiltonian, we just get the lowest eigenvalue of this Hamiltonian will be the case excited state, or the case excited states of the original Hamiltonian. So yeah, we have this trial state, and if we try to calculate this expectation value, we can just expand the equation like this. So yeah, here our intention is to find a better beta I. So like from this equation, we can see that in order to guarantee this beta, in order to guarantee the minimum, or like the minimum of this function to be the case excited state, we need to choose beta I to be at least greater than ek minus ei. Ek minus ei, because yeah, we can just, if we look into this equation just very attentively, we might be able to reason why this needs to be greater than ek minus ei. But there's one problem, like we don't know the value of ek, because it's the value we would like to estimate. So we don't know the value of ek, so just choosing this beta I could be difficult. So we can use we can get this information from like in another way. That is, this ek minus ei is greater than is less than or equals to the gap between the maximum eigenvalue and the ground state energy. And we also don't know this maximum eigenvalue, so we kind of estimate it with like the spectral norm of the Hamiltonian. So this could be represented in this form, and we can just choose ek minus ei to be based on this value. But still, this value is still large, and there are like some other papers that are trying to find a beta I, like a better guess for beta I, that will result in like a lower cost. And one good thing about choosing beta I is, even though we choose like a wrong beta I, if we do the optimization and finally we will get the result to be the difference between those two. So if we chose a beta I which is less than ek minus ei, from the result we can just tell if we made a wrong choice or right. So that's one good thing about this way of choosing beta I. It's kind of self-correcting. So yeah, that's how we choose the beta I. And the other thing is, we talked about how to choose this beta I. The other like extension is calculating this state overlap, right? So in order to calculate the state overlap, there are two possible way of doing it. One is just to use the swap test, and using swap test requires additional number of qubits. So there are two ways. Like if we want a lower number of qubits, we can use this method. And if we want like a lower Daves method, we can use this method. And yeah, like to calculate the overlap, what they suggested in this paper is the destructive swap test. And yeah, we can just apply C naught from those two are like this. The upper one is the first state, and the lower is the second state. So we can use this destructive swap test to measure the state overlap. And the lower number of qubit method is first we're just planning to calculate this state overlap, right? And what we can do is this phi k could be represented as a state preparation. So from a zero state, we can apply a certain rotation or the certain unit rate transformation to prepare that phi k. And this could be prepared by the dagger of this state. So finally, if we just see this part of the circuit, or like this part of the circuit, it's like applying from zero state, just from zero state, applying a certain dagger of unitary and another unitary transformation. And finally, from the measurement outcome, we can just, the overlap with zero state is just choosing those measurement results that are 0-bit strings. So it could easily be calculated without any additional qubits using this method. So we can prepare the state in this form, and then from the measurement value, we can just take the fraction of the bit strings that are measured to be as 0 in the computational phase. So these are the two methods for measuring the state overlap. So yeah, that's all about VQD. The second algorithm is subspace search VQE. So the main idea in subspace search VQE is like unitary transformations, they preserve orthogonality of state, which means if we have two states, initial state, and we apply a certain unitary transformation, the angle between those two initial states is going to be conserved. So that, so they kind of started from this idea. And let's say we have k initial states, k initial orthogonal states, and we have the Hamiltonian operator, and we have k eigenstates of the Hamiltonian. So the problem here is to search for a certain unitary transformation that maps these k initial orthogonal state into the eigenstate of the Hamiltonian, which are like both are orthogonal. So the problem here is to find a proper setting that is suitable for searching this unitary transformation that maps these orthogonal initial state into the eigenstate of the Hamiltonian. So a proper setting for this could be just all about what we need to do all is like on the cost function. So the first here, if we see this equation, it's called the weighted subspace search VQE to find the case excited state. Here, what we need to find is the unitary transformation. So like here, if we see, we have from 0 to k minus 1. Okay, yeah. From 0, so from 0 to k minus 1. These are like these indexes are, they corresponds to the like the initial state that we're considering. For example, the index 0 corresponds to the ground state, 1 corresponds to the first eigenstate, 2, like, so it increases just accordingly. And if we use this cost function and try to optimize it using VQE, and finally we get a certain parameter for this unitary transformation, right? Then if we apply this unitary transformation into the initial state, that is going to map it into the corresponding eigenstate of the Hamiltonian. So yeah, these the difference between those two is this cost function setting, it allows us to find all the eigenstates of the k eigenstate of the Hamiltonian with just one optimization loop. And this one will allow us to find the only the case excited state energy. So these are like the two ways of setting up the cost function and running the VQE to calculate the excited state energy using subspace search VQE. So this is it. And yeah, what are the pros and cons of subspace search VQE? uh, this one is really easy to implement because we don't need like even a deeper circuit or like additional qubits. So it seems to be NISQ friendly, and there's no any hyperparameters that we need to deal with like VQD. And the optimization is also just like a one or twice. But there's like a really big problem with this subspace search VQE, that is choosing a reasonable ansatz could be difficult because here, like we're in the normal VQE, we just need a unitary that maps like that search for the ground state energy. But here, the problem is kind of like complicated because we're mapping K initial state into another K state. So it looks that this unitary has to be very expressible and difficult to prepare it. So yeah, and so this in turn affects the performance of the algorithm, although it works reasonably well in principle. And yeah, and optimizing this cost function is also difficult. Like it seems a little bit complicated cost function. So these are one of like the two major drawbacks of subspace search VQ. And finally, there's one thing we need to consider as like finding we might not be interested in all excited state energies of a given Hamiltonian. For example, given a certain Hamiltonian operator, there are like 2 raised to n eigenstates, right? But if we try to find each eigenstate iteratively, it could be like really cost-consuming process. So what we can do is we can just skip some of the we can just find these eigenstate that we are particularly interested by adding some constraint or some penalty terms. So this is called like a symmetry operator, like by adding some term on the cost function. And this method could be applied both on VQD and subspace search VQE. So one symmetry operator could be like spin. For example, if we're interested in the excited state with a particular spin, we can calculate the expectation value of that spin operator, and then if it's not within such constraint, the cost function is going to be penalized. So throughout the optimization loop, like it makes it really easy to find the excited states or the eigenstates that we are particularly interested. Okay, yeah, so that's it. And here is the numerical results of those two papers. Yeah, this one uses the VQD to find the excited state energy of, I think it's H2, yeah, H2 molecule. And this is the result from subspace search VQE to find the excited state energy. Okay, thank you. If you have any questions.
Was under the second algorithm.
The second?
Which maps.
Okay. Yeah, this one?
Yeah, this one. Isn't the whole point of this one to find eigenstates? I mean, what I'm trying to say is, can we use this one to solve the first problem? So if I find the eigenstates from this one, then I can find the eigenvalues.
Yeah.
And the whole point for the first algorithm is to find the eigenvalues.
Yeah, okay, right, yeah. I mean, like, here, just if you find here, like, the eigenstate, which means you have the Hamiltonian operator and just measure the expectation value that gives you the ground state energy. For example, like, you use the ansatz or like the ansatz to prepare the ground state, like the ground state energy, and then you evaluate the ground state energy by calculating the expectation value. So here is, yeah, what it's trying to do is you have like some randomly initiated initial state. It's not like you don't find these orthogonal initial state. You can just randomly set up some orthogonal state, and then you try to search for a certain unitary that maps those two initial orthogonal states into the eigenstates of the Hamiltonian.
Each eigenstate corresponds to some initial, right?
Yeah, but these initials are like some randomly that you can choose some randomly, like as an initial state. And then this unitary is parameterized. So the whole point is to find the parameter theta. If you find the parameter theta, then you can apply this unitary on the first initial state, and it gives you the first eigenstate of the Hamiltonian. And you apply this unitary on the second initial state, and it gives you the second eigenstate of the Hamiltonian.
Okay, so afterwards that I found the unitary.
Yeah, so
I can find the energy eigenstates, right?
Yeah, okay.
And then I can find the energy eigenvalues.
Yeah, that's right.
So can I use them to solve the first problem?
I didn't understand what you mean by
this is the second problem, subspace search.
Oh, this is actually both algorithms, they solve the same problem. So yeah, so like those are two alternatives, like that both, like the first one has its own drawback, and this has some advantage. So like those are like choosing which algorithm is better, like what I'm trying to show is, so just basically you have a Hamiltonian operator. That's just a matrix, and it has eigenvalues, right? Just like you might have n eigenvalues. Using VQE, you can find the lowest eigenvalue, and these are the algorithms that are used to find like the other eigenvalues that have higher, like the rest of the eigenvalues that are greater than the ground state, or like the lowest eigenvalue. So yeah, these are, and this algorithm allows you to find all the eigenstates or all the eigenvalues simultaneously through one optimization loop, but just by searching for this unitary transformation.
I see. But the first algorithm is
the
not
first
one shot, right?
Yeah, the first algorithm, like you use it iteratively. You find the ground state, and then you use that one and find the second largest eigenvalue, and then you use both of them, and then find the third lowest, the third lowest eigenvalue. Then you use it iteratively to find the k eigenvalues of the Hamiltonian.
Also wanted to ask you this, I think slide 4 has this picture, or not?
Yeah.
Maybe slide 7. I'm not sure.
Yeah.
Here.
Okay.
I was wondering, what's the depth of the circuit?
Depth of the circuit? Here, it's actually like if you see the cost, this is the cost function, and if you see the first equation, it's just normal expectation value measurement of the Hamiltonian. So it's same as the original VQE, the ordinary VQE. But the Debs is kind of a problem. Like in order to calculate this cost function, you need to calculate both this term and the second term, right? And the second term is measured by, like this state overlap is measured by some, like either swap test or the method I showed in the next, like in this slide here. There are two ways of estimating this overlap. The first one is using swap test. The second one is just by applying the inverse of the first state preparation, which is like the Debs is kind of twice of the first, the VQE. The one disadvantage of this method is it requires like longer circuit Debs, which is.
So overall, how does it compare with the coherence time of our device?
Yeah.
And what I'm trying to find, is it reasonable to implement the algorithm, or is it like 10 times longer than the coherence time?
Yeah, actually, yeah. Even there are some like research and some simulation results. They actually use this algorithm on actual hardware, just only for a small system, and get a reasonable result with an chemical accuracy. But the problem is when you increase the size of the problem, this circuit is going to be like deeper. So there's a limit that you cannot go further if it takes on the limit of the capability of the hardware you have. So it's kind of, yeah, it's one of the like the disadvantage, or like just one it's kind of the cost of using this method to find the state overlap.
I see. And here, when we do the state overlap, we overlap only the states whose eigenvalues we have previously solved.
Yeah.
So if I solve ground and first excited, I can only do their overlap.
That's right. Yeah, you do the overlap with the first and the second one, the ground and the first excited. For example, you wanted to find the third excited state, right? The second excited state, right? So you have the ground state and the first excited state. So you need to find the overlap between the first excited state and the second, and with the ground state. But this, since you already saved the parameters, you can do this problems in parallel. So if we have like a lot of like a quantum, a lot of devices, so you can even just make it you can even use it efficiently without some extra cost on like the runtime or something.
So I can solve the problem parallel.
Yeah. Like that's one advantage of using this. So you can here, like these are cost overlap estimations, right? So I think you can calculate these overlap states just in parallel, because if we save the optimal parameter of each state, and these are like just if you save the optimal state of each the optimal parameter of each state, so you prepare like each eigenstates or each the previously calculated eigenstate in parallel, and then you have the current calculated like lambda k, and prepare phi k, and then just calculate the state of each of them in parallel. But like it requires a lot of resources.
One question. I think I'm confused. For first algorithm, we find only the eigenvalue, right?
Yeah.
We don't. So do we find the eigenstate afterwards?
I guess if you find like the do I have a marker? Oh yeah, here it is. So yeah, like just for first you start from you start from a certain state, and the state preparation is like it could be something like this, right? So this is the eigenstate. If you have the optimal parameter, this is the eigenstate, and the eigenvalue is.
But I think this is second algorithm, no? Or this is first algorithm?
Even with the first algorithm, the method is to use, like you just transform this, for example, for the k's eigenvalue, you just have this of lambda k. And if you start from the initial state, then it's going to be. So this is the k's eigenstate. And if you want to find the eigenvalue of this, what you need to do is which is like you rotate the basis. This is like if you have the initial 0 states, this is the unitary transformation. So here you have the eigenstate, like this the whole system, this quantum system represents the eigenstate. So if you want to find the eigenvalue or the expectation value, you just do this like basis rotation and then measure each qubit. HQE. You just make the measurement, and from that measurement statistics, you can find the eigenvalue that corresponds to this eigenvalue.
I see. So I got confused, and we find the eigenstate before we find the eigenvalue.
Yeah, just technically that's right.
Yeah, but how? For example, if you only know ground state, how do you find the eigenstate for first excited state?
What?
The unitary transformation.
Okay, yeah. So
how do you know?
I mean, here, like, we're more of interested in, like, if you see the application, what you need is mostly the energy gap between certain, like, excited, the energy gap between two states. So you might not be that much interested about like the eigenstate here, like if you see the application. But here, like, you have the eigenstate, but you don't need to know the eigenstate. You just find the eigenvalue. So through the optimization loop, like, just you measure the expectation value of the Hamiltonian, right? So this value is important in the cost function or in the optimization loop. So yeah, what we are more interested in is in this value.
So we know the eigenstate beforehand.
Yeah, here, like, if you find this optimal parameter, and you apply this unitary transformation, so the state that you're gonna have here is the eigenstate, like the lowest eigenstate of the Hamiltonian.
Okay. I couldn't figure how do we get the eigenstate. So.
Okay, yeah. So just the state here it corresponds to the eigenstate. If you have maybe like can explain it more in simple terms. Yeah, if you have some idea, just try to. Okay. Eight?
Yeah.
This is eight. This is eight, right?
Yeah.
Okay.
I also want to go to the question for why the spectrum of optics can be represented as the profound of the
Actually, I'm not sure, but yeah, I don't know like the detail here, but the spectral norm corresponds to the maximum eigenvalue of the Hamiltonian operator, right? So it's kind of bounded by. Yeah, I'm not sure. Like, need to say the detail, but yeah, the gap will be upper bounded by the spectral norm of the Hamiltonian, I guess. Right? I'm not sure if you have like any. Lambda, right? Maximum lambda. Oh, okay. So yeah, okay. Those two is like the difference will be bounded by maximum lambda and my minimum lambda, and the maximum lambda is same as the norm, right? So that's why I think it should be given as this. Yeah, I'm not sure if it's like satisfactory answer, but yeah, I think like that. Yeah, the energy gap between the maximum and the minimum is. Okay. So like here, we kind of shift into this problem because here, like, what our interest is to find the gap ek minus ei, and we don't know about the value of ek, so we need to estimate, need to make some like a closer guess to this gap. So that's how it went to this direction to find the better like estimate for this gap.
So my question is that can VQE like find energies of degenerate states too.
Yeah.
Yeah, and can that be like verified that they are like, energies from degenerate states?
Okay, yeah, I think that's uh, I mean, like here, I think if you use like maybe I like tried subspace search like for simulation thing. Like if you're going step by step and once like yeah, like for example, if you see the subspace search here, so the total cost function, if you see it here, like it will find all the like it will try to find all the eigenvalues that minimize the whole cost function, right? So if we try to solve this cost like this cost function, finally you might find the states that gives degenerate eigenvalues. I guess finally, yeah, because just if you simply see the mathematical representation and see the like the corresponding unitary transformation, and if you try to calculate the expectation value of each transformed orthogonal state, they might correspond to the yeah. I think yeah, it gives sometimes it gives uh, this kind of results, but it might be hard to find it practically, I guess.
And also, it's just like one random question. So when you have to find the theta and prepare the state, does that prepared state actually mean any like is it like relevant to actual physical system, or is it just like a random state that gives you some correct like expectation value?
One thing is like one possible application for VQE is it could be kind of a state preparation circuit for QPE. Actually, QPE is the like using QPE you can find the eigenstate, the eigenvalue of a certain unitary operator, right? With a certain trial state here. So like, but here, if you see the application, what you'll be mostly interested in is like the expectation value, and then trying to find gap most of the time between the eigenstates. But like yeah, so maybe the eigenstate that corresponds to the like the minimum, like the ground state of the Hamiltonian could be sometimes for a better accuracy, they might be used as an initial state for QP to find the eigenvalue. Am I answering it right, or like?
Yeah, I guess it was yeah. Can you go to slide 13?
Slide?
Yeah, slide 13.
13.
So you talked about how we can add constraint terms to the cost function to create the symmetry.
Yeah.
Are there any ansatz that enforce the symmetry, like parity preserving or number preserving?
Yeah. Actually, there are there is actually there are answers that preserve the number of particles or number of electrons, but here when you find that's actually one using an answer that preserves the number of particles is kind of one thing. You don't even you might not even consider it as like finding eigenstate of particular interest. Yeah, how do I say that? Yeah, like that's one thing. There are ansatz that preserves the number of particles. That's one step. You can enforce it through the ansatz. You don't need this kind of additional terms. What we need here is, even though the number of particles is preserved, but we might be interested in some other symmetry sectors. which cannot be enforced by the ansatz.
Right. Is that true? So is there a symmetry that you can't preserve using? Like, is there always, shouldn't there be always be ways to
maybe
enforce the
like they could be I mean they could be a state that like the okay, for example, even though you might use some ansatz, for example, a hardware efficient ansatz. Like you use the hardware efficient ansatz for like its different advantage. For example, maybe because of running it in the hardware. So you're not using this ansatz to preserve this symmetry. So you might add like these constraint terms, but like not always. Like if you try to preserve all symmetries and use that kind of ansatz, it might have like some drawbacks.
Right.
So that's why I think this term is added. But I'm not sure if there's a symmetry that cannot be preserved by.
I was just curious because like I was wondering if there is a general rule of thumb if adding extra terms is better or using strong ansatz is better.
Yeah, I actually that's a kind of a trade-off, right? Because like one drawback of using hardware efficient ansatz is it doesn't preserve like the symmetry, so it's kind of like vulnerable to bare inflatable problems.
Yeah.
But like the other problem of using these symmetry preserving ansatz is it adds like some additional costs. For example, if you see UCCSD and other like these ansatz that preserve like this kind of symmetry, they have their own like cost or like additional gates in order to like enforce these symmetries. So there's a drawback. So if you're not using a symmetry preserving ansatz, you can add this additional cost. This additional term is also has like some cost because you're measuring expectation value of this.
Right. So the measurement cost.
Yeah, measurement cost. Yeah, that's right. Yeah. So just adjusting the trade-off is really important. More question? No? Okay. Thanks for coming. There's no anyone on Zoom, right?